Hey everybody, I hope you're having a good day. Today we are going to move forward in our Unit 7, Note Packet 7, and we're actually going to move away from mole conversions for the moment, although they'll still be a part of what we're doing. And we're going to start to learn a new calculation, which is the percent composition by mass calculation. So if you would like to take notes along with me, we should be on page 3 in Note Packet 7. And I think it says like percent composition at the top. We're basically going to take that page of notes and then the back of that page, page 4. And then you're going to work on a virtual lab since I'm not there, obviously, to push out the actual lab to you. But we'll do the virtual version instead. All right, let me just share my screen and then we'll go ahead and talk about the percent by mass calculation. All right. Okay, so let me just kind of introduce you to this. There we go. All right. So basically, the equation that we're going to be working with today is right here, and it is on the back of your reference table in Table T. And basically what it tells us is the percent by mass of either a certain atom or a certain element in the particles of a molecule, or the percent by mass of an element in a mole of molecules. So we'll talk about it in both ways. So let's start what I think is a little bit simpler. Let's pretend we had one water molecule. Here it is right here. What this calculation might tell us is out of the mass of the entire water molecule, what percentage of that mass comes from the oxygen atom? Or out of that entire water molecule, what percentage of the mass of that molecule comes from the hydrogen atoms? So if you look at the percent by mass formula, you'll see that percent composition by mass is calculated by taking the mass of the part, whatever part you're looking for, the oxygen or the hydrogens in a water molecule, dividing it by the mass of the whole thing. That'll give you a decimal. And then to turn that into a percentage, you need to multiply the resulting decimal by 100. Okay, so for our purposes, the mass of the whole thing would be the GFM. So there it is again. We're going to use it in today's calculation. So let's talk about why we're going to use the GFM in today's calculation. Okay, so this should be at the start of page 3 in your notes. So when we do the percent by mass calculation, we could, if we wanted to, do this calculation for an individual molecule. So we could figure out the percent by mass of, say, oxygen in one individual water molecule. But often this is kind of silly because we might want to talk about more than just one single water molecule. That is a very small sample of a substance. What we might want to talk about instead is the percent by mass of an element in a mole of molecules. So when we look at a chemical formula like MgCl2, we can kind of think of it two ways. We can think of it as if I had one individual magnesium chloride molecule, there's one magnesium atom in that molecule for every 2 chlorine atoms. Or we could think about it in terms of the subscripts, the 1 and the 2 in this case, giving us the mole ratios of each element in that particular compound. So what that means is the mole ratios is if I had 1 mole of magnesium chloride molecules, which means I would have 6.02 times 10 to the 23rd magnesium chloride molecules. For every 1 mole of magnesium atoms I would have in those molecules, the 6.02 times 10 to the 23rd of them, I would have 2 moles, twice as many moles of chlorine atoms. So what this mole ratio thing is all about is I'm saying to you, if you look at the formula for a chemical compound, like that of magnesium chloride, and you think about it not in terms of representing one individual molecule, but instead representing an entire mole of molecules, what we're saying is there's 1 mole of magnesium atoms per every 2 moles of chlorine atoms in this many molecules of the substance. Okay, so that's the idea. So basically, when we do this percent by mass calculation, if we're thinking of it in terms of moles of molecules, the whole point of this calculation, like I kind of started with, is that we can tell the percent by mass of each element in a mole of molecules of a given substance. Like I mentioned, you'll probably memorize it anyways, but this formula is on the back of your reference table in Table T. Oops. All right, so let's look at how this would work. So maybe just take a moment and I'll kind of pause. If you're taking notes, perhaps write down, calculate the GFM, the total mass of HgCl2. All right, so calculate the GFM total mass. That's going to be our step 1. All right, so basically why this is our step 1 is, again, we're trying to think about doing this calculation for a mole of molecules of a given substance, 6.02 times 10 to the 23rd of them. And if we wanted the mass of the entire mole, or the mass of the whole sample, the mass of that 1 mole of particles, well, that's calculated by the gram formula mass calculation. So what I'm saying to you is step 1, to get the mass of the whole, what we're really doing is we're getting the GFM of the substance. Okay, so we get the mass of the whole thing, the GFM. If we did it for this calculation, the sample one that I'm asking us about, it says determine the percent composition of mercury and chlorine in mercury 2 chloride, which is HgCl2. So to get the mass of the whole thing, again, we're getting the GFM. We'd say, all right, we have mercury and chlorine in this compound. There is 1 Hg for every 2 Cls. I would multiply the number of atoms of each element by the rounded mass from the periodic table of elements. And I would get for this substance, the mass of the entire mole, the mass of the whole thing, is 271 grams per mole. Okay, step 1, get the GFM. Okay, so from here, let me just back up a second. Let me do it like this because I don't really like how I had it in the notes. Let's say if I wanted the percent by mass of mercury in this entire mole of HgCl2 molecules. So once I get the GFM, that's the mass of the whole thing. The equation I'm using is the mass of the part over the mass of the whole times 100. Okay, well, if I was doing this for the mass of the part, I wanted the percent by mass of mercury in this, a mole of these molecules. Out of that whole 271 grams of mass, 201 of those came from the mercury. So this is basically what my setup would look like. The mass of the part, what you're looking for. In this case, we said it was mercury. That's 201. Of that 271, the whole came from mercury. That would give you a decimal. That one multiplied by 100 would turn that into a percentage. Okay. So if I wanted to do this for instead chlorine, this would look a little bit different. It's still part over whole times 100. The whole mass of the whole thing is still the GFM, which for this substance is 271. But you have to look carefully at your GFM setup. Of that 271 grams of mass per 1 mole, 35 times 2 or 70 of those grams came from the chlorine. So it'd be the mass of the part, if we were looking for chlorine's percent by mass. In this case, it's 70, over the mass of the whole thing, which is 271 times 100. And that would give us the percent by mass of chlorine in this compound. So basically that's what you see here in step 2 in the notes is me just showing that setup, but basically combined. The top is for if I wanted to do this for mercury. The bottom is for if I wanted to do this for chlorine. It's the same setup I just went through on the previous slide, a little bit more broken down. Okay, so that's basically the calculation. Now we're going to run this sample calculation, and then we are going to take it up a notch. So stay with me, because this is not the end of what we're going to learn today. And then we'll try this in a lab. All right, so let's do like another calculation. This says, what is the approximate mass by percentage or percent by mass of potassium in KHCO3? Okay, so I need to use the percent by mass formula. So that's part over whole times 100. The mass of the part over the mass of the whole times 100. To get the mass of the whole, assuming I have 1 mole of molecules of this substance, which I'm always going to assume, I calculate the GFM for this thing. So we should be good at this by now. In this formula, we have potassium, hydrogen, carbon, and oxygen. There's 1 K, 1 H, 1 C, and 3 O's. I would then multiply the number of atoms of each element by the rounded mass from the periodic table of elements. Potassium's mass rounds to 39, hydrogen's to 1, carbon's to 12, oxygen's to 16. And you're going to have to trust me here. When you add all that together, this is going to come out to be 100 grams per mole. So the mass of the whole thing is 100 grams per 1 mole of particles of this substance. All right, well, now that I know the mass of the whole thing, I can put the mass of the whole, which in this case is 100, in the denominator. The mass of the part, well, I'm looking for the percent by mass of potassium in this compound. So in a mole of atoms of this compound. So I would look at my GFM calculation and just focus on the potassium. Of that 100 total grams of mass, 39 of them come from the potassium. So the part, 39, over the whole thing, 100. Don't forget to multiply by 100 to convert the decimal back into a percentage. I just realized I left my calculator in the other room. I'm going to have to go grab it for the next thing we're going to talk about, but I can do this one in my head, because 39 divided by 100 times 100 is 39%. So the percent by mass of potassium in this compound would be about 39%. 39% of the mass comes from the potassium. The rest of it, the 61%, would come from the other atoms that make up the particles of this substance. Okay, so that's the idea. So we're going to take it up a notch. Just waiting a second here to make sure everybody got that down, although it is in the completed notes. Okay, so it's not over yet. Now we're going to talk about what a hydrate is. So I think this is on the next page in your notes. And this is where we're going to end today. We're going to talk about what a hydrate is. We're going to do a practice setup for a hydrate, and then we're switching over to the lab. All right, let me just really quickly, I'm going to need my calculator for this. I think, maybe not, but just to be sure, let me just grab it. Okay, got it right here. All right, so what's a hydrate? Well, if you think about it, if you were going to hydrate, right, best thing to drink is probably water, right? So there are some compounds, some substances out there whose particles have been hydrated, like literally water molecules are part of the structure of these substances. So they're compounds, typically a crystalline one. So that means it's a combination of a metal and a non-metal, an ionic compound, where water molecules are literally chemically bound, or they're like attached to that substance. So if you were going to look at like what it would look like this would be a good example. You have some ionic compound where water molecules are literally like bound to it. It's attached to it. So an example would be this. This is actually, I believe, the substance in the lab you're going to do. This is copper sulfate, CuSO4, copper 2 sulfate. That's been hydrated. It has like literal water molecules surrounding each of these CuSO4 molecules. So formulas for hydrates look kind of funky. They look like this. It's like the formula for the ionic compound, and there's like a dot, And then there would be like a number, like say 3H2O. So that dot, it doesn't mean multiply. You could kind of think of it meaning like attached. Sorry, I'm using my finger. I don't have a stylus. Attached to. Okay. So like in the hydrated form of this substance, right? Hydrated CuSO4, hydrate. For every CuSO4 molecule, what this formula would be translated as attached to it are 3 water molecules. So basically the virtual lab, you're gonna observe. You can take a hydrate and turn it into an anhydrous salt. That says anhydrous salt. Basically, you can remove the water, and that's what this is representing here. The hydrate right here on the right, where the water has been removed to produce just the anhydrous salt, just in this case, the CuSO4. And that can be done very simply by heating up the substance with a Bunsen burner, a hot plate, some form of heat. All right, so what's a hydrate? A hydrate's a substance that has literal water molecules attached as part of its structure. And then you can take a hydrate and turn it into an anhydrous salt. By heating it, it removes the water, leaving just the salt behind. So you can do a percent by mass calculation for a hydrate. So we're going to run through one of these. Remember, this is in your notes because you're going to have to do this in the lab. So if you're confused on how to do it, look back in your notes. All right. There's a few ways to set something like this up. I'm going to recommend you consider setting it up the way I'm going to show you because it'll just make it easier to see. You'll see what I mean in a second. All right. So I want to know the percent by mass of water in this hydrate. CuSO4, which attached to each of those molecules this time are 6 water molecules. This would be called a hexahydrate because there's 6 waters per each copper sulfate molecule. All right, so to get the percent by mass, which is what we're asked to calculate of the water, we're going to use that same equation, the mass of the part over the mass of the whole times 100. So we still have to get to the mass of the whole thing first, which means we're going to get the GFM of this substance. Now, here's where I really recommend you just embrace my setup. I write down the formula for the hydrate that I'm given. So CuSO4, and attached to that, each of those CuSO4 are 6 water molecules. And then in my setup, I usually just kind of split it, and I do the mass of the CuSO4, the salt, separate from that of the mass of the water molecules that are attached to it. And you'll see why I do that in just a second. So what I'm saying to you is don't try to like do it all together. You can, but I think this is easier. I'm also using my fingers, so bear with me. All right, so like I would do the GFM of the Cu, S, and O. There's 1 Cu, 1 S, and 4 O's here. You're going to have to trust me. Copper's mass rounds to 64. Sulfur's mass rounds to 32. And hopefully by now you're starting to remember that oxygen's mass rounds to 16. So I'm going to add that up. 4 times 16 is 64, plus another 64 is 128, plus another 32 is 160, I think. Pretty sure about that. So that totals out to 160. All right, so then I'm going to do this again, but for 6 waters. So I just have hydrogen and oxygen and water. If I had 6 waters attached to each copper sulfate, there are 12 hydrogens total, 6 times 2, and 6 oxygens total. Hydrogen's mass on the periodic table rounds to 1, oxygen's mass rounds to 16. 6 times 16 is 96, plus 12 more is 108. I better double check my math because 64 plus 32 is, 160. And then, I'm right. Okay. So to get the mass of the whole thing, right, because that's our next step, is the part over the whole, the mass of the part over the whole times 100. The mass of the whole thing is the combined mass of the copper sulfate, 160, plus the mass of those 6 waters. So that would be 268. So you'd have to add them together to get the mass of the whole. The reason why we set this up like this is now it's very easy to see that 108 grams of that total mass, we're asking for the percent by mass of water, 108 grams out of that 268 grams comes from those 6 waters. I'm going to put that in my calculator, and I'm going to make sure I multiply the resulting decimal by 100 to turn it into a percentage. So 108 divided by 268 is 0.429 blah, blah, blah times 100. When rounded to the tenths, this comes out to be 40.3%. So 40.3% of that hydrate, CuSO4.6H2Os, is the percent by mass of water in that hydrate is about 40.3%. Okay, that is the idea. Biggest tip I have for you is to calculate the mass of the salt, in this case the CuSO4, separate from that of the mass of the water, the 6 waters in this case, and then it should be easier to figure out the setup for finding, say, the water or the salt's percent by mass. All right, this should be in the completed notes. It is in the completed notes that I posted on Classroom. So if you need to go back and reference that, make sure you do, or look at your own notes packet. You're going to need to do this in the lab. So here's a really good sample problem for you. All right, so where are you going next? You're now going to go to Google Classroom, and you're please going to work on Lab 21, which is called Hydrate Calculations. It is a virtual lab. I'm sorry I'm not there, but we're still going to do it, and you'll generally still get the idea of what the lab would be like, which is good. And more importantly, you're going to run the calculations for the lab, which is the practice you need for this calculation. Remember, Mr. Nagel, he is here to help. He is a retired chemistry teacher, so you can call him over. He knows his stuff. He can help you. So please take advantage of the fact that he is there, and just do your best. I know you can do it. All right, guys, good luck. Please go work on Lab 21 hydrate calculations, and I'll see you as soon as I can. Bye, everybody.